All right, let's start. We just finished the quiz 1, and then so for the quiz statistics, so we got the 96% for the average score. So as I expected, so the purpose of the quiz is about not testing your knowledge at that time. So I want to make you to keep all the knowledges from the quiz forever. So that's why I designed the quiz like that. And then I'm happy that the most of the students are doing great. And then, so today we will learn about the SSL and TLS, secure socket layer and transportation layer security. So we are getting out of cryptography stuff. And then the reason why we learned about the esoteric cryptography is to learn about the basis about how our internet is secured. And then internally, the SSL and TLS, they are using symmetric crypto, asymmetric crypto, and HMAC inside there. And then they will also use digital certificate and PKI. And then we will see how the real implementation of the network security utilize what kind of the technologies in there. And then before getting into the details of the SSL and TLS, let's do recap about the digital certificate. And the digital certificate is a file that contains some of the entity's information. And then we use that to authenticate whether the other end is the right person that we are talking to. So it cannot be a person, it could be a business or just a computer or something like that. And then what this digital certificate has in their field is that there's a common name that serves as an entity identity. So we use that, we call that as a CN, common name. And then because this certificate is for serving website, any kind of website hosted by OregonState.edu domain. So that's why it says the common name, the entity name is this one. And then the certificate is issued and signed by some other trusted entity. So we have a chain of the certificate, and then that composes the PKI. And then that's why the certificate also includes the issuer information. And then issuer also has the identity name, and then it could be some of the company name or something like that. Yeah. And then the most important part is that if we are not, so we are actually binding some sort of the public key to some of the entity name. Yeah. So what it does is this in common RSA, this company certifies that the OregonState.edu has the specific public key written in this certificate. And then to prove that this certificate is valid or something, so what the issuer does is try to run the cryptographic hash on the entire content of the certificate, and then sign that hash with their private key. And then that serves as a digital certificate that the in common RSA checked that and verified the identity, and the public key is bounded. And then this certificate has a trust chain. So the OregonState.edu certificate was signed by the in common RSA CA, and then in common RSA CA is signed by user trust RSA CA, and then user trust RSA CA is a self-signed. So how our public key infrastructure is constructed is that there is a leaf node. It could be OregonState.edu, and also for my website, unexploitable.systems, it also has a leaf node certificate. And then that is certified by some other entity, and then another entity, up and up and up. And then usually it does not have more than 7 hops or something. So usually I think 2-3 hops are the most popular, most common. Yeah. So in our example, it was Oregon State, in common, and then user trust. And then at the root, there could be no entity to verify that root entity itself. And then in that case, we use the self-signed certificate. And then for this kind of to bootstrap this kind of the PKI, our community chooses some of the good company operates as a root CA. So they can sign their self-signed certificate, and then they can sign some other certificate, but there has been some of the incidents of like the stolen private key for this kind of the certificate generation. So in that case, that company, so those kind of company will never exist after the kind of the incident. Yeah, that's how the PKI and trust chain works in reality. Any questions about the digital certificate and PKI? Yes. Who is secure? What? You can see all that, like the incoming RSA server, trust RSA website. Yes. So if you connect to any kind of website, I can demonstrate that right now. So how can you do that? Is I'll share the entire screen. Then let's do it with Google Chrome. And then, so this is a CTF that unexploitable the system. Oh, so it's still playing the thing. Now you can see the screen, right? Yeah. So this is our scoring server. Then if you get into there, there's something mentioned that connection is secure. Then says the certificate is valid. And then my website, this is like the certified by with this domain name. And then that is signed by the Let's Encrypt. And then, so R3 Let's Encrypt the certificate is signed by another root CA. So all of the HTTPS based website. So here, HTTPS, that's important. All of the HTTPS website should have like this kind of the certificate chain. And then whenever we connect to the server, we verify that. Actually, we are learning the details of the steps today. Yeah. And then another interesting thing is like so people that Oregon State.edu, they don't use HTTPS. Yeah, it's hard to find like the HTTP only website these days. Then it says not secure. And then because the connection is not encrypted at all and there's no certificate, so it is saying something like that. And then so it's still connecting. So there's no HTTPS for this website. I don't know why. Yeah, but almost all of the websites. So this website belongs to the Zoom. Yeah, and then it also has certificate information, and then you can check all these kind of info. Yeah, but I usually see only like the 2 or 3 hops, but yeah, maybe there could be like the 7 or 8 hops. I don't know, but yeah, we usually stay with the 2 or 3 hops for that. Yeah. And we can get that. Yes. And then the next is Diffie-Hellman. So if this slide has too much text, please ignore that. Just focus on like the user A need to choose a small a, but they need to send like the computed value. Yeah, not the raw value of the small a. And then the user B chooses the small b, and then they will compute with the public material and then generate some of the value. And then if they share these values, then they can share this secret while the other entities don't know about either A, neither of A or B. Yeah, they cannot generate the same secret. Yeah. So the implication of the Diffie-Hellman key exchange algorithm is that 2 entities can securely can exchange a shared secret over the communication channel. Yeah, without leaking the shared secret at all. So the importance is that like the beauty of like the exponentation, yeah, that gives like the both entities can easily calculate the G over AB, but the attackers or other entities, they can never get this information because like the simple algebra will result in like these kind of the different result. And then it is proved that the discrete logarithm algorithm, So to solve that, the known existing algorithm, their complexity is too high. So like we can use that as a cryptography. But the problem is that like if the quantum supremacy is done and then there's a quantum computing, general quantum computers are available, then like the quantum computers are very good to find the sum of the periodic values. And then you will see that there's a modulo operation. And then that means like based on the number P, it will periodically have the same value over and over again. So in that kind of the structure, the quantum computers are very good at solving this kind of problem. So when the quantum computing comes in, then we cannot use this simple or elliptic curve-based Diffie-Hellman exchange. And then after we learn about how we can protect, provide some certain property to the network communication, for example, authentication, we can do authentication and then checking authenticity of the other entity by using the digital certificate and PKI. And then by relying on that, we can do key exchange without worrying about the man-in-the-middle attack. Yeah. So that I will show the man-in-the-middle slide again. Oh, there's no slide here. So please recall that suppose there's one person and the A and B, they would like to communicate each other, but the internet is structured like any kind of the middleman could be there. And then if there's a middleman C, tries to talk to A and B and then replay the messages from A to B and then B to A, then A and B cannot know that they are directly talking to each other, or there's some of the middleman delivers all the messages. Yeah. So to avoid that kind of the middleman attack, what we can do is like when we are doing Diffie-Hellman material exchange, we will ask both end sign their Diffie-Hellman material. Then we can verify that that value is directly coming from the end, not by the middleman, because the middleman does not have the private key, so they cannot generate the correct signature. So we can kill the man-in-the-middle attack by using the digital certificate and then relying on the PKI. And then after that, after having the Diffie-Hellman key exchange, we have the sum of the number, random number, shared between two entities. And then based on that random number, we can generate several keys. So the one easy way to generate the, for example, suppose we need a 1000 byte key. And then with the Diffie-Hellman exchange, we only have 32 bytes. Then we can create the 1000 byte by doing something like this. Run SHA-256 using the shared secret. Then we will have the value. And then run that with the hash again. Then we will have another 32 byte. And then run the hash with the output again and again. Then we can run the SHA-256 again and again to generate the arbitrary number of the values starting from the shared secret. Yeah, that's the way that we can generate the several keys from the one derived secrets, and then we will see more details about that later part of the lecture. And then after having a shared secret, that means that we can have the agreed key for the symmetric cipher and also for the HMAC, message authentication code. So we can provide a confidentiality to the communication channel by running the symmetric crypto by generating some of the keys, something like just put the cipher key and then add the shared secret. Then that hash could serve as a AES key. And also for providing integrity, we need to have a key for the HMAC. And then we can also generate the SHA-256 MAC key or like some other value. And then using the shared secret, then we can have the key for MAC. So after that, we can send all the messages like this. Yeah. So basically, digital certificates, key exchange algorithm, Diffie-Hellman, symmetric cipher, and HMAC, message authentication code. So by mixing these four algorithms and techniques, so we can establish communication channel that supports authenticity checking, confidentiality of the data, integrity of the data. Yeah. Any questions for like the constructing secure communication channel in this manner? Yes. So suppose like the the simple reason is like we have a one shared secret, but we need a symmetric cipher key and then HMAC key. We want to have a different key. Yeah. And then the one way to generate is it's something like a deriving the key. And then the characteristics of the cryptographic hash function is that even if you know the symmetric cipher key, you cannot guess what's the number of this one, right? Yeah. So that's the one way that we can use like this. And then based on this number, and then we use the different string at the start, then it will result in a different result. So that we could have so it's something like from a shared secret, we can securely derive the two different keys. Yeah. And then the cryptographers has proven that if the hash function is a pseudorandom function, PRF, then this is secure. And then you will see that internally in TLS, we are actually doing the same thing, similar thing in there. So I also have seen that like can you just use this, something like naive like this, but it's secure. Yeah. Any other questions? So we just have seen that like the simple version of the secure communication channel, and then today we will learn about how our internet is actually doing something for providing the security over the network. So the topics for today are we will start with that. I will start with the stating that the internet is insecure. So when the internet is designed in 1970s, their goal was like to make it work. Yeah, I believe like almost all of the product and these days also like getting out like the first just to make it work, and then later think about the security. But that demonstrates the failure of the internet, and then like how hard to fix that at the later time. So in these days, like if we design a new infrastructure, something like the internet or something else, then like we do like care about the security at the start, at the design point. But in the old days, we cannot have like a luxury like that. So at that time, make it something work for the communication was like the top priority. So the internet was insecure. We will see about that. And then because the internet was insecure in 1995, some company called Netscape. How many of you have heard about Netscape? Oh, there are some. Yeah, I was surprised because like that was my first web browser that I have used in like the 4th grade in 1995. Yeah, yeah. I'm not sure like still we can download the Netscape or not, but that was the most popular web browser and at that time, and then the developers knew that like the internet is insecure, so they would like to provide some sort of the network security, so that they developed the library called the secure socket layer, and then that was good. So later it was standardized by the internet IETF, Internet Engineering Task Force. Yeah, they standardize it as a transportation layer security. So basically SSL and TLS, these are the same thing. Yeah, SSL 1.0, 2.0, 3.0, then standardized as a TLS 1.0, and then now we are using TLS 1.3. Yeah. And then let's get into details. So let's take a look at the internet first. So the internet is internet. So it's basically a network of networks. So there are many networks, and then internet is like it's just connecting across the multiple networks. And then the reason why we do that is, so right now on the internet, I can connect to any kind of website in the world. Yeah. But to think about how we can enable that. So suppose there are big n number of the websites, and then myself, and then if I, and then websites, and then they are communicating, it can communicate. If we are enabling like the communicating, all the pairs are like the connected, then that requires like the ON square kind of the topology. Yeah. And then there could be so many devices. I believe like there are several billions number of the cell phones, and then there are several billions number of the computers. And then if we construct the ON square network for entire computers, then like that would not survive because N square is too big for that. But to take a look at so that this is the structure of the internet, but to take a look at this kind of the part. So on the right side, there are like a small 10 megabps Ethernet LAN kind of thing. So for this kind of so this is actually the router, and then it has 4 computers. So for this kind of the 4 computers, 10 computers, or 100 computers, yeah. So for managing small network, having an ON square topology is not that burden, but we do not have like that kind of the fully connected topology. So we also see that like it has like the ON complexity for like the connecting the servers, computers. So basically the concept is like if we fully connect entire computers, that could be super complex. So what the design principle of the internet is like create a small local network, small enough that can manage as an ON square, and then create another layer of the network of network, and then that will have like the small number, for example, 100 or 256 as n, and then having an n square. And then it will have another tier, and then it will just manage that network again and again. So the concept is like making the small n and small m, that number small. Yeah. So the implication is that I told you at in the 1970s, make it work is the most important thing. So to have a lower complexity to make it work, so they need to make it simple. I believe like many of you have seen this kind of the diagram, so-called OSI layer. So this is a layer defined by the network engineers. So in computer networking, we have several different parts. So the physical layer means actually the media. So what kind of the cable do we use? So it could be UTP cable, or it could be wireless 2.4 gigahertz or something like that. That means the physical layer. And then data link layer means that, have you heard about the Ethernet or MAC address, those kind of thing? So that kind of protocol to searching for the local network falls into the data link. And then network layer is about the IP. So if you heard about like an IP address, and then that falls into the third layer. And then maybe you might heard about like you need to know the IP address and port to connect to some of the service. And then that falls into the transport layer, because the TCP, UDP, that kind of protocol uses port. Yeah. And then like we don't do much about the session and presentation layer. So in old days, when we work with the slow communication channel, for example, using a phone line to do some of the internet or something, and then for that kind of communication, we do have some of the signal compression mechanism over the phone channel, because the phone line is too slow. With the compression, we could have like a much more efficient communication. So we previously use a lot about like a presentation layer, but these days we don't use that. Yeah, because like the one main reason is like if we encrypt the data. Yeah. So can you guess what will happen if we encrypt, if we compress encrypted data? So if you compress a regular text data, the size will be reduced to 1/3 or half or something like that. Yeah. So that's right. So if you encrypt 1 megabyte of data and then try to compress that, then you will see that your archive file will have definitely a bigger size than the original file. So the reason is, so we measure the how dense is the data as a so-called entropy. Yeah. And then the most of the text data or like the unencrypted data, they do not use like the fully utilize the entire space of the information can be stored into certain size. But what encryption does is like it tries to maximize the entropy and then look like a random number. That's the basic concept of the cryptography. So the cryptography is directly countering. So the compression is something like, so there is a less dense data and then try to encode that into specific format to be more dense and then higher entropy. And then what encryption does is like try to maximize the entropy so that nobody knows about this data. Yeah. So like if we try to compress it, then we cannot do that. Yeah. So presentation layer is mostly about the compression. Yeah. But because we will implement the transportation layer security in session and in between the session and presentation layer. So after the encryption, we cannot use the compression. So that's why. And then interesting thing is that they say there's an encryption at the presentation layer, but when we do transport or network data link and these kind of things, there's no encryption at all, no security. So that's why we need to implement security of the internet communication, not at the internet, but at the software layer, because the entire internet structure is not designed to have security at all. And then to have a better understanding about the enemies on the internet, potential enemies. Yeah, I'm not regarding the everybody is malicious, but there could be some of the malicious hosts over the internet. But to understand some of the threat model, let's take a look at how a packet can be routed over the internet. So in this map, suppose your computer is at here. So your computer is at here, and then my computer is at here. And then your computer would like to send one of the packet to me. Then how it goes is that you will put some of the data in your computer, and then you will send it. Then it will go to the router first. Yeah. So you might have at your home, your Wi-Fi router is there. Then it's something like if you want to send the file, it goes to your Wi-Fi router first. And then that is connected to some of the line, for example, CenturyLink. Yeah. Then it will go to the regional ISP, which is a central, for example, CenturyLink for the Corvallis. And then it will send the packet to upper level internet service provider. ISP is the internet service provider, maybe the Comcast or Google or like a more bigger internet service provider. And then so suppose I was at the outside of the United States, then it must go through the underwater cable to transmit the packet to the opposite side of the world. And then how that works is like there's a so-called internet exchange point. And then the internet service providers are competing each other to process the packet because they are actually paying each other for how many packets are processed. So that there's a so-called internet exchange point. So you can think it as like some of the auction market or something. Yeah. So there's a list of packets and then list of the price, and then they just route all the things. Yeah. And then it goes to another big ISP. So my home, I connect with the Wave G something like the connection. So that could be one of the ISP. Then it will come to my Wi-Fi router, and then I can access the file. So I just simplify the steps, but usually there are 10 or 20 steps if the one user and the other user communicate each other. Yeah. So we just briefly show that have seen that like how a packet can be routed. But the important thing here is that this is totally insecure. So when we are using the internet, we mostly use a TCP as a communication channel. And then TCP does not have encryption by default. So this is the one of the packet that I captured last night, and then like my MacBook Pro is communicating to one of my Apple TV in my home, and then you can see data in plain text, right? So these are encoded, not the encrypted data, because you can identify some of the numbers, characters in there. So that this kind of information, it's just there. But we have seen that when you send the packet to me, then it will go over several routers, right? And then what if a router is malicious and then they can read all your packets? Then they can read your password or some other private information. Yeah, that's possible if we are not using SSL TLS. And then another bigger threat is that, so the router, the middleman, can redirect the packet to anywhere. So when one person send the packet to the other person, we do not specify the route. The router choose where to send the packet to the next step. Then, for example, what if one of this router, while you are sending the packet to me with this path, so one of the router send the packet to the completely different server, so we cannot prevent that. That could happen. In that case, this computer knows the contents of your packet. So the internet is designed like this. So it's totally insecure, and this is totally possible. So I believe like I hope you understand like the internet is so insecure, and then it is just designed as like a simple, and then just make it work. Yeah. So let's take a look at the internet without SSL and TLS. Yeah. So suppose there's a user, and then there's a server, and then suppose I want to search a dog. Then the packet will go over the insecure communication channel. Then it will go to first router. Then the first router knows that I searched a dog. It will redirect it to the second router. And then they also know I searched a dog. And then the third router is the same. And then the server will get the result. Yeah. And then the server will prepare the search result. And then it will send back. Same thing. They can all see the search result. Yeah. Yeah. That's the internet before 1995, how that works. Yeah. So the implication is that on the internet, there are so many middlemen, but everybody in the middle knows what I searched. And then also for the search result, that means like they can see every single content, every single characters in the packet. Yeah. So that's so insecure. Then how can SSL TLS change this? So suppose we establish a secure communication channel by checking the certificate to verify the other end, if that end is a correct server or not. And then we use the Diffie-Hellman exchange with the digital signature, so authenticated. So kill all the man-in-the-middle attack. And then after sharing secret, we will use symmetric cipher and HMAC. So making nobody in the middle can know about the content. If anybody in the middle change the content, then we can detect it. Yeah. And then because we do certificate-based authentication, so middlemen will never know about the Diffie-Hellman shared key. Then the result might be, so in the middleman, they know that I am connecting to that server because that IP address part is not encrypted at all. Yeah. So that they know that I'm communicating with that search server, but that they don't know what I've searched and then what was the search result. So conceptually, we are creating a secure communication channel. And then whenever I search dog, and then I will generate an encrypted message for that. and then send that to over the internet. So all the middlemen will see this random number. They don't know about this, but the other end can decrypt it. And then the server decrypt it and run the search and then prepare the image, but they need to encrypt it again. Yeah. And then it will send over the internet. Yeah. Yeah. And then I can decrypt and then get the result. And then nobody in the middle know about the result, and then nobody in the middle can change the data. If the change happens, then I can verify with MAC, HMAC. Yeah. So the implication is that by having certificate verification, key exchange, and then symmetric cipher and HMAC, the middlemen will only see the encrypted content. They don't know about the content, and then they cannot even alter the content. So this kind of concept, secure socket layer, was developed by Netscape in 1995. Oh, there was a question. So the question from Zoom was like, could we ever encrypt an IP address? So there are some of the approaches for encrypting the phone numbers. Yeah. So like you can regard IP address as something similar to phone number. So, but it's very hard to encrypt the phone number itself, is that, or IP address itself, is that there are many middle routers, but if they don't know about which IP address it should send to, then there are some of the algorithms, so-called like the oblivious routing or something, but we can do that. But the problem is that as far as I know, the fastest oblivious routing, if we implement that over the internet, then our internet will be 1 million times slower. Yeah. So that we cannot wait for a few days for sending one Discord message. Then like if you ask a question, then like a due date will be passed already. Yeah. So that's why we cannot do that. But for the efficiency reason, like we do not encrypt the IP address at all. But there are some of the approaches to have like some of the anonymous communication. Yeah, in that case, like we can masquerade the IP address. Another question. All right, yes. So that we can actually masquerade ourselves is something like there's a onion routing, so-called like there are many routers, and then like what we can do is like we can ask them to route the packet weirdly, so that like the other end can never know about like what was the IP address of myself. They can only see the IP address of the routing network. Another question. So the thing is like have you heard about like SIGINT? So in 2011, do you know Edward Snowden? So that guy was a whistleblower of the U.S. government. So like that guy was working as a system administrator for a defense contractor, and then like that guy collected information about some of the U.S. confidential information from government, and then figured out that the U.S. government are running so-called SIGINT as an operation. And then what that means is that like most of the data are encrypted, but they try to collect the metadata, such as a phone number or IP address, and then who talks to whom, and then try to figure out some sort of the information out of it. Even if they don't know about the data, just collecting the metadata, they would like to utilize that to for the intelligence service. So that there are some of the good thing about we can use that information to counter the terrorist activity or something like that. But the same thing can be used for launch a surveillance to any kind of citizens, something like that. Yeah. So there were problem of having that kind of the metadata leaked, so that there are some of the folks who would like to work with the making the IP or phone number totally anonymous and private. But practically, I believe it's quite hard to implement. Yeah. So all right. So the SSL was like the project in a single company, Netscape. Yeah. But the Netscape was you can think it as a de facto standard web browser. Yeah, I'm not sure. Like nowadays, like it was Google Chrome in 2005 to 2010-ish, but right now we use Safari, Edge, Chrome. Like I believe like their market share is like somewhat similar. I believe Chrome is the best, but it's not about like a 90% or something. But in 1995, like the Netscape Navigator was like the 95% or like more market share was owned by them. So if they do that, then that could be a standard. But the important thing is like the SSL was good. Yeah, and then that's why IETF, yeah, they standardized that as a standard. And then you can take a look at about the details of the standard as a RFC document. So for the internet, so any technology that we are using is documented by the IETF RFC. RFC stands for request for comments. So the original developer of that technology describes about the specification of the thing. So if you're interested in about the more details about the TLS, then please take a look at the RFC document. And then, why is it called as a transportation layer security? So the transport layer security. So transport layer, it supports a TCP, UDP, and that kind of protocols. And then in this diagram, TLS is implemented in session and presentation layer. Indeed, it is done by this. But why do we call it as a transport layer security? So that term is coming from the difference between the OSI layer model and then internet TCP/IP layer model. So in the TCP/IP layer model, there's a network interface, and then that is like the physical and data link layer. These two are directly matching to the network interface. And then network layer is the same network layer between two. And then transport layers are the same. But in the TCP/IP model, they regard all these session presentation application as an application. Yeah. And then actually where the transport layer security sits is in between the application and the transport layer. Yeah. That's why we are calling it as a transport layer security. So anything above the transport layer will be protected by transport layer security and then go down. Yeah. So that's the thing. And then the most important thing is that the transport layer security would like to be transparent to the application. And then what that means is that, so we would like to add encryption in the middle, but the requirement is that we want to minimize the changes in the application. So if the application is not changed at all, and then if we just plug the encryption and if that works, then that will be perfect. Yeah. But the actual design is not that simple, but the engineers have designed this TLS to have a minimal fix in the application code. At the end of this lecture, I will show you that the difference between the regular socket communication and then TLS socket communication, and then you will see that there are minimal differences between two. Yeah. And then the reason why the transparency is important is that if we can support the transparent transport layer security, then applications do not have to change the behavior, so cost is very cheap. Yeah. Then next, then what an SSL or a TLS can do. Yeah. So that basically they just can establish a secure communication between two ends. Yeah. Two end could be client and server, server and server, client, client, but in HTTPS or in our regular daily computer use, we mostly use a client and server communication for TLS. Yeah. And then we usually use TLS for verifying the server entity. So the reason is that so think about the scenario that I'm connecting to some of the website. So I know myself. Yeah, that is not changing. So that I don't have to verify myself. And then I would like to verify the server entity. So That's why I do not have digital certificate. So you guys do not have the digital certificate too, right? But you can use digital certificate of the target server to verify the target server identity. So in using TLS, so it supports the mutual authentication. So we can verify two ends, but we usually verify the identity of the server, and then after establishing the secure communication channel, we verify ourselves to that server by username, password, or that kind of the manner. So the authentication is we use a TLS for authenticating the server only for that, and then we will do authentication of ourselves in the application of the server. And then what it can enable is end-to-end secure communication channel. What that means is that we have two ends, the client and the server, and then we would like to send packets. Then there are so many middlemen, but we would like to make that the packet is not revealed by any middlemen and then not altered by any middlemen. So end-to-end security. And then to have the end-to-end security, they provide these kind of properties: authenticity, confidentiality, and integrity. And specifically, we use the technologies that to verify authenticity, use digital certificate, and then do key exchange with the Diffie element, and then symmetric cipher and HMAC. And then let's go over H by H about how SSL TLS indeed support these kind of the properties. So first is authenticity. So we usually use the SSL TLS to verify the other end server identity because the packet routing could be arbitrary. We cannot control that. Yeah, any router can route the packet to google.com to somewhere else, to the North Korea. That's also possible. Yeah. So we don't want that. And then we would like to communicate with the target server directly. And then authenticity checking is done by the digital certificate and PKI. Yeah. So SSL TLS first verifies that if the server has the PKI verified as digital certificate with the same domain name. So for example, if we connect to the www.oregonstate.edu, then we need to download the certificate of the desk server, and then we need to verify that the domain name is the correct. Yeah. So if you connect to the google.com, then you will see the certificate that the CN is stated as a google.com. If you use the oregonstate.edu certificate for google.com connection, then that will be rejected by the TLS library. So the first steps are decomposed as 3 steps. So to have the authentication, yeah. So we need to get the server certificate, but that there are 2 more steps that we are doing. So that there are 2 more preliminary steps for setting up for the TLS communication. And then these are called the client hello and server hello. So it's something like, if I want to connect to the google.com, then I will send the client hello first. And then that includes the what kind of the TLS version I'm using. So we need to talk with the same version. Yeah. So that's why. So the client hello, I can say like I'm using TLS version 1. Yeah. And then client sends some the random number, and then also sends some of the available cipher suites that I can use. Then the server also sends the random number, and then some of the version number, and then also like the server chooses like which cipher suite that it will use. And then that preliminary step is required before sending the certificate. And then let's take a look at more detail about each of the things. So this is the packet capture hex dump of the client hello. And then if you use the Wireshark application, then you can see the packet content in a structured manner. And then this is the client hello message. So it's actually the interpretation of the data on the left side. And then it says, I will use TLS 1.2 as a version. And then I'm sending some of the random number. And then the reason why we send the random number is that we want to make each connection unique from the previous connection and then the other connection, because we will use the same private key or something like that. So by having the random number, and then we will use that for generating the keys. So the random number will affect to the each time we connect to the server again, then we will refresh the key, something like that. Yeah. And then client also send cipher suites. And then this is something like suppose you have an OpenSSL, which is a TLS library, and then that library can support all sorts of the cipher suites. But in some cases, you would like to use like a smaller library or restrict the number of the available cipher suites, because like some of the cryptography requires like the hard computation time. So you want to use like some of the efficient encryption algorithm for low power systems. Yeah. So to support that kind of thing, there's a lot of choices, and then like the client is free to send like the list of the cipher suites to the server side. And then most of the cipher suites are written as TLS, ECDHE, RSA with something like this. And then we will learn about the details of each message. But to briefly introduce about this, so TLS means that we are using TLS. ECDHE is elliptic curve based Diffie-Hellman, ephemeral. So this part describes about the key exchange algorithm. RSA, this part describes about what is the digital signature algorithm. And then AES-128, that defines what is the symmetric cipher. And then GCM is the mode. So you can see CBC here, GCM here. We didn't know about the GCM, but you can regard GCM similar to the counter mode, CTR. Yeah. And then SHA-256 as an HMAC algorithm. So these cipher suites actually defines key exchange, digital signature, symmetric cipher, block cipher mode, and HMAC, how we will do the HMAC. Yeah. And then after client send the version, random number, and these kinds of cipher suites, server receives that, and then server will reply to the client about the server will also send some of the random number to refresh the connection. So the reason why both the server and client send the random is that like suppose you don't send random number. Yeah. Suppose the only client send the random number, but the insecure client may use the same random number again and again, then like the entire connection will be fried. Yeah. So it's something like even if the client is dumb, they just reuse the same number again and again. If the server is sane and then they provide some other random number, then the entire connection could be refreshed. So that's why both ends send the random number to establish the connection. And then among all these like the cipher suites, server has chosen that the ECDHE RSA is 128, GCM, SHA-256. Yeah. So there are a list of the available cipher suites from the client side, and then server will choose one. But the important thing here is that the server has the configuration that like do not use the cipher suites below certain level of the security. For example, DES, that's still available in OpenSSL library. So we can use that for TLS, but we know that the DES has a 56 bits of the key, and then it's quite insecure. We can decrypt it. So if you try to connect to the TLS-based server, and then just giving the cipher suites about the DES, then server will reject the communication. Yeah. So there's a mechanism that even if the client would like to reduce the security of the entire cipher, but the server will not allow that. So it's something like client offers a cipher suite and the server will choose it. Yeah. And after exchange this kind of the preliminary material, then the server will send the certificate. And then from here, you will see that the certificate is in certificates. There are several certificates in there. And then it has 4 certificates, entirely 6 kilobyte or something. And then it sends the full chain of the certificate. So this is the packet capture when I connect to the oregonstate.edu, so you will see that the first certificate is for common name is oregonstate.edu. Next is the income on RSA, and next is the user trust RSA. I don't know why this one is there, because this one is a self-signed, so we don't need the last one, but I believe the server configuration has that certificate too. Yeah. So basically, after client hello, server will send the entire chain of the certificate. Then at the client side, we can verify that by going up for PKI, the PKI tree, and then like at the end, if we have the root CA certificate for this one, then we can verify that. Any questions for the client hello, and then server sends the certificate, and then client verifies the certificate at server identity. That's the part. Just having the authenticity problem, just resolving the authenticity problem. And then next step after finishing the authenticity was like key exchange. Yeah. And then in old days, client choose the key and then send to the server. And then that's possible because server has the public key based cryptography. And then we have the server's certificate. That means we know the server's public key. Then to agree a shared secret, what we can do is, so client knows the server's public key written in the certificate. And then client can choose random key and then encrypt that with the server's public key and then send that to the server. Then public key crypto guarantees that only the private key holder can see this message. So only the server can see that key. Yeah. So that's how the TLS, SSL works. But in these days, we don't do that because there's another important property, so-called the forward secrecy. So suppose we are doing that when we agreeing the shared secret. So we don't do Diffie Hellman, and then client choose a random number and then send that over the network by encrypting using the public key. Then let's assume that suppose the server's private key has stolen maybe 3 years later. Yeah. Then attackers can decrypt all prior data because clients choose a random key and then send that over the network with the encrypting with the public key. And then if we have that capture, and then 3 years later, if we stole that private key, then we can decrypt all the data. Yeah. And then that means this scheme does not guarantee forward secrecy. And then now you will be curious about what is the forward secrecy. So forward secrecy, and it is also called as a perfect forward secrecy. Then what that means is that, so we will use a long-term key. Long-term key here is a server's private key to establish a secure communication channel. And then 3 years later, that could be stolen, maybe. But at this time, we are communicating a lot with the creating sessions. Then, even if the private key got stolen at a certain point, can we make all prior, like the communication, unable to be decrypted by the attacker? Yeah. So the reason for having this was there for like a long time, starting from 1990s, but due to many practical reasons, the people didn't implement that in the early stage. Yeah, but because in these days we have a lot of the software and hardware vulnerabilities, and then one of the great example was that the SSL TLS library. The library itself has a information disclosure vulnerability, and then that vulnerability was called a Heartbleed. Yeah, and then in 2014, that vulnerability was discovered. And then what you can do is, if you can connect to any kind of website and then send the malicious packet, then you can take a look at the part of the memory in the server. So that sometimes leaks the other users' username and password because we share the memory. And then sometimes it leaks the private key. Yeah. So stealing of the private key is feasible scenario in this era with the vulnerability and the hacking kind of activity. So the forward secrecy is very important. Yeah. So to have the forward secrecy in key exchange, TLS uses ephemeral Diffie-Hellman. Yeah. So here, ephemeral Diffie-Hellman is that we will use one-time value for the Diffie-Hellman key exchange. So let me explain this more correctly. So in Diffie-Hellman key exchange, user and the server will choose A and B respectively, right? And then these are private key. Nobody knows. Then is there any reason that we need to refresh that? So we can use the same value again and again. Yeah. But here we are assuming the scenario that one of the private key could be stolen. So in that case, how we will do is we will use random A and random B at any time we connect to we establish the channel. In that case, even if one of the private key got stolen, you will never know what kind of the private key material was used in the key exchange. Yeah. That's how we can establish the perfect forward secrecy. So it's not that difficult. Just change the Diffie-Hellman material every time. So that will guarantee the perfect forward secrecy. Yeah. So we call that the Diffie-Hellman exchange used in the TLS as a ECDHE. So that's the most popular algorithm right now. And then that stands for elliptic curve based. So like we are not using discrete logarithm. So we are using the elliptic curve based on discrete logarithm. And then we will do the Diffie-Hellman exchange over that. And then the last ephemeral means that we will change the private key every time we make the connection. Yeah. So even if one session got compromised, then attacker can never guess another A, another B, yeah, in the private communication. So we can keep the forward secrecy. And then let's link that with the SSL TLS steps. So there was a client hello, and then server hello, and then server will send the certificate. And then after that, server will send the server key exchange message. And then that is the message that shares the Diffie-Hellman material to initiate the key exchange. Yeah. And then when sending the Diffie-Hellman material, server need to sign this one with the private key. So this part is incorrect, the signed by the private key. Yeah. And then the reason why we sign Diffie-Hellman material with the private key is that this value is indeed generated by the target server, not by the middleman. Yeah. So let's take a look at the server key exchange message. So server key exchange, and then from the Cypher suite, we know that they are using ECDHE RSA something, right? So they send ECDH, right? Elliptic curve Diffie-Hellman material, and then key length is 65 bytes. So that they create a private value B, and then generate a G over B mode P, and then that value is this one. Yeah. And then that value is signed with the RSA, and then fingerprint algorithm is as SHA-512. So what that means is that it will hash this public key using SHA-512, and then using server's private key RSA algorithm to generate the signature of this public material. So this Diffie-Hellman material is authenticated number. And then right after that, server send the server hello dawn. So this packet is a very small, the 4 byte. And then the purpose of this message is that server, I don't have any message to send, so now it's your time, something like that. Yeah. So we have go over up to step 5. So we have until step 10. Yeah. but we will go over that. So up to this point, what we can do is that now the client can verify the server's certificate. They know the public key, yeah, and then they can verify the signature of the Diffie-Hellman material, and then they can share a secret using the Diffie-Hellman material. So the authenticated secure key exchange is done, not yet done at step 5. And then, so one of the weaknesses about the Diffie-Hellman was the man-in-the-middle attack. Something like the middleman can work like this, but we can kill that attack with the digital signature out here. Any questions? Yes. So server does not change RSA public key. So that is fixed in the digital certificate. But in Diffie-Hellman exchange, so G and P are public. And then A and B are private. So they don't change public G and P, but they will change B and A every time makes a new connection. Yeah, so they only change A and B, not about the G and P. So that will result, this public part of the Diffie-Hellman exchange will be changing every time. Yeah. So we finish it up to this point. So that, and then next is about the client part for finishing Diffie-Hellman exchange, and then starting encryption. And then let's go over that. So step 5, until step 5, server has sent their key material to us, and then we can authenticate that. Yeah, and then the client also need to send the Diffie-Hellman material to the other hand. So that message is client key exchange. Yeah, and then in here there's no signature, because in this kind of the authentication we only authenticate the server. We are not authenticate the client. So we just send the Diffie-Hellman public material. Yeah. And then after sending this message, both end, server and client, can calculate the shared secret. Yeah, because server has the client's material, and then client has the server material. Yeah. So after sending this message, clients generate the session keys. So client don't know B of the ECDHE. It actually know G over B mod P. Yeah, but they can calculate the session keys. And then in TLS, how both end calculate the session key is with this fashion. So to generate the key material, this is directly excerpted from the RFC of the TLS version 1.2, compute. So that this is the key. And then here, PRF. So the PRF here means that pseudo-random function. And then we can use any kind of the pseudo-random function, because this is a standard. It's quite neutral for that. But we will use SHA-256 as a PRF. And then here, security parameters are master secret. This master secret, that means the shared secret over the Diffie-Hellman key exchange. So we will put that as the input of the hash, and then we will use just a normal string key expansion. So the same thing happens in the real TLS, right? So, but using that is secure. Cryptographers have proven that if PRF is secure, then use of the key generation like this is secure. That is mathematically proven. And then it will also add server random, client random to refresh. Even if all the other materials are same, we will refresh the random values, so the key will be totally different per each time of the connection. And then we will use this PRF until enough length of the output is generated. So what we can do is that we can run hash one time with this one, then we will have 32-byte output. And then we can hash it this value again. Then we will have another 32-byte. we can add that value again. Then we can keep generating 32, 32, 32, 32 values, the byte of the blocks. Then we can generate the arbitrary length of the key bytes. And then after generating enough bytes, it will generate the client write MAC key. So this is for HMAC. And then server write MAC key, client write key, server write key, and then client server IBs. So that it actually generates two keys for when clients send the packet to the server, they will use client write key. When the server sends the packet to the client, they will use a server write key. And then they will use the corresponding IB and then HMAC key for the server write and then client write. And then the reason why we separate out client and server key is that like the trying to identify who wrote that message. So if that is decrypted by server write key, then we know that the original writer of that message is the server. Yeah. So the shared secret goes to here, and then client random, server random from the client and server hello goes to there. Yeah, that's how we generate the keys for the symmetric cipher and HMAC after we do the key exchange with the DPL. And then after that, client also knows that server will have the same value, expect that. And then it will send 1 byte message. Yeah, change cipher spec. And then I don't know why the message name is something like this. And then actually the meaning of the change cipher spec is something like telling the server that from now on, I will send the encrypted packet only. So that's the indication of the change cipher spec. So it's indicating that I'm ready to encrypt and decrypt everything. So from now on, I want to do the encrypted communication. Yeah. And then right after sending this change cipher spec message from the client, and then client will send the encrypted handshake message. And then this step is to verify if client have calculated all the values correctly and then give the proof to the server. So it's something like client to let the server know that I calculate this value, and then you will know that I have the same key with you, something like that. And to do that, what it does is like the compute a SHA-256 of hash of the concatenation of the all handshake message. So what that means is that we have these messages. So when creating the number 8, so we collect all the packet data of the 1 to 7 and then hash it. Yeah, it will include the client random, server random, cipher suit, what has been chosen. So entire message will be hashed. Yeah, and then it will compute SHA-256 shared secret, client finish it, and that hash, and then just take 12 bytes. And then do some of the operations, but the important thing is that what client is doing is that hash the entire traffic that the server and client exchange, and also hash the master secret and do something and then send that to the server. And then these are all based on the information that server also has. So all the packet information, they exchange it all together. So the server has all the content, and then server also has the shared secret. Yeah, and then they can calculate the same value. So if the client sent to the server and then server calculated value, these are the same, then the server can verify that client has the correct key. And then the most important part is that after hashing the thing, it will be encrypted with the AES. So what server will do is like after getting the encrypted handshake message number 8, then they will decrypt it. And then suppose there's a decrypted value. And then they will recompute the same value and then compare with it. That means our key is correct, right? So that's how the client can verify, give a proof that this server that we have the same key. So because the value is encrypted, so it's totally encrypted like this. So you can see that the encrypted handshake message is here. Yeah. So that's the client part for making themselves ready for the encrypted communication. Yeah. And then, so at this time, after server receives the client key exchange, server is also ready for doing the encrypted communication. So they also send change cipher spec to client, let client know about that. I will also talk in encrypted. Yeah. And then finally, they also send encrypted handshake message to the client to give a proof that the server has also calculated all the value correctly. Yeah. So 9-0, the 9-0 is that like the client send the encrypted handshake message. So the server need to decrypt it and then compare the value. And then if that value is correct, then server can send the client that the change cipher spec. So now the server is also ready to communicating in an encrypted communication. And then after that, server will send the similar thing. So for client, it includes from message 1 to 7, because message 8 was the encrypted handshake message. But in the server side, it will compute from message 1 to 9. Yeah, because this is message 10. Yeah, so it'll hash that in the same manner, but it will use different message. So that was client finish it for the client encrypted handshake message. But in this case, we will use a server finish it. So the value is different. But so even if client send the correct proof, the server cannot send the same proof to the client. Server has to calculate the exact value and then generate this value. And then later, the client can verify that. And then after all these stuff, all these communications are finished without any kind of error, then that means client verify the server, and then they exchange the shared secret, and then they generate the keys for symmetric and MAC correctly, and then now they can communicate. So with these 10 steps, it's a little more complex than like what we have learned, but conceptually, it's just simple as 4 steps: authenticity, key exchange, symmetric cipher, and HMAC. So they do that to establish secure communication channel in TLS. So after that, they can just send the encrypted data. So what they do is both always says encrypted data and MAC. And then server will use server write key, and then client will use client write key. Any questions for the TLS protocol details? You don't have to memorize all, because like I will not do that kind of quiz, because it will be also open material, so you don't have to worry about that. So the important thing is like you have seen that each of the steps, and then you know the important part of the authenticity check, key exchange, integrity, and confidentiality, and then how we support that in the TLS. All right, then let's move on to the next. So we have seen the cipher suit, and then now I believe you all know about like what each part of the thing means. So ECDHE RSA is 128 GCM SHA-256. That means the first part is about the key exchange algorithm. And then second part is the digital signature algorithm. And then TP-Hellman material will be signed with the RSA. And then after sharing a master secret, we will generate the symmetric cipher key and then MAC key. And then for the symmetric cipher, we will use AES 128 GCM. And then for HMAC, we will use SHA-256. That's what these kind of the cipher suits means. And then another interesting thing is that in SSL TLS, we can have an option to not using some of the part. So there is a cipher suit, ECDHE non AES 128. In that case, we don't do digital signature authentication. Yeah, that's totally insecure, so we don't use that, but there's an option to like having that kind of thing. And also there's an option that the AES GCM none. So like in some cases for like the reducing the power consumption or something, yeah, some folks who don't want to have like integrity protection, then like they can ignore the SHA-256 as a none. Then like the server, both the server and client will not attach MAC for the sending messages, but that will lose the integrity protection. So the important thing is TLS is quite flexible to let it, like both the server and client can choose like a whatever crypto, but they need to negotiate because client sent the list of the cipher suit, but the server choose one of them. So they need to negotiate to make this secure communication need to be established. And then let's analyze why is it secure. So one of the attack that we have seen is like on the internet, it's like that there are many routers, and then what man in the middle can do. So there's no man in the middle in this kind of communication because client verifies server certificate at step 3. Yeah. And then that means that they need to have the correct certificate, and then that is certified PKI. So to have a man in the middle, they need to fool or hack the entire PKI. Yeah. So that's possible, but that's hard to do. That's why we trust like the PKI, and then based on that, we can verify the server's public key and then identity. And then we will verify server's digital signature. So the verifying the digital signature means that we are checking that the server is a holder of the private key. And then that means that server is the server in the certificate. Yeah. So that's how we authenticate the server. So if the middleman cannot have the private key of the server, then they cannot do man in the middle. Yeah. And then another thing is like any middleman, could they guess the key? So all the exchange messages are public. So these are not encrypted before sending the change cipher spec on each end. So for these kind of messages from message 1 to 7, it's not encrypted at all. So that any middleman can see that. Then the question could be, can that kind of middleman guess the key? Just take a look at the publicly available unencrypted traffic. So the guessing is very hard because the master secret is shared securely via ECDHE. Yeah. So the attackers will never know that. Yeah. And then man in the middle is also has been killed by the digital certificate, the digital signature verification. And then there could be some of the replay attack. For example, there was a one session, and then suppose that session was hacked, so the session key was leaked. But in the next time we connect to the server, both client and server will send different random number. Yeah. Then we cannot reuse that key. Yeah. So the reason why we insert server and client random is to kill that kind of replay attack. And then the reason why we are inserting both random from the both side is like even if one side is not putting the random number, yeah, then we can make the connection secure if the one end send the random number correctly. Yeah. And then we are using pseudo-random function as a SHA-256 and a SHA-384, which is like believed as a secure for right now. So like I believe there's no luck for like even if like the part of the value or something, you cannot guess about the master secret, or you cannot guess about the output keys. And then another discussion point is like why do we hash all the previous messages? Yeah. So like this is for like having the correct communications. So for some protocols, we know how the protocol starts. So for example, for HTTP, it starts with the get, put, or that kind of the plain text message. So if we decrypt the thing and then decrypt the data is random or something, then we know that the key is wrong. But when we transmit the data between two parties, yeah, data could be random too. Yeah. In that case, we cannot verify the decrypted result is correct or not. Yeah. So the important thing is that before starting any kind of communication, clients wants to know that the server has the correct key, and then server wants to know that the client has the correct key. And then the reason why it hashes all the previous communication messages that by doing so, if there's any change in the bit or byte in the message, because those kind of the exchange messages. So the messages from 1 to 7, these are not encrypted, not protected. That means any of the middlemen, they can change the value. Yeah. So the attackers can change the value and then make them calculate the wrong encryption value. And then eventually, if another key is decrypted by, so suppose one of the server encrypt one of the client encrypt the message as a get. But by altering this kind of the exchange message, if the attacker can make the server decrypt this message, not get, as a put, then that could be a serious problem. So the get is reading the thing and the put is putting them like a file on it. So it's doing the totally different thing. So the reason why we hash all the previous messages is that there is a chance, there's a high chance then any kind of middleman can alter the exchange, the protocol message. Yeah. And then these protocol messages are unprotected. So that's why we need to verify that all the values that I'm seeing is the same on the server side. Yeah. And then the next is about the application of the SSL and TLS. So we can use SSL TLS for any kind of the TCP communication, but the most popular usage is using in HTTP. So HTTP is a hypertext transfer protocol, and then you can regard that as the protocol for the web surfing. Yeah. So the World Wide Web, yeah, is based on the HTTP. Whenever you connect to one of the website, they talk with the HTTP protocol. But here, the important thing is that the HTTP : / So this directive means that your web browser will directly talk to the browsers using HTTP. No encryption, no protection. But HTTPS, that means that the browser will use TLS to communicate HTTP. So they shoot the plain text HTTP message over TLS, not on the regular TCP. And how can they do that? So I emphasized about transparency in the application, and then please keep that in mind. So let me show you one of the example of how the HTTP works. So there's your web browser, and then there's a server, and then HTTP, in HTTP, it directly talks to the server. And then how that works is that, so suppose I want to get the root page with website from the server, then I will send the get HTTP message like this. So / means that give me the top of the website, top directory. Yeah. And then I will just send this. Then server has the content, HTTP 200, okay, and then some of the data. Yeah. And then they directly send that to me. And then that's how it works. And then any of the middlemen can see the content of all these protocols. This is how HTTP works, and then it's not protected at all. So it was something like this. And then applying TLS looks something like this. So the web browser will use TLS, and then TLS, between these TLS, we will communicate over the encrypted data, but actually the browser send the plain text HTTP to TLS. And then TLS will encrypt that and send that to over the other end. And then this TLS module will decrypt the data So the server will see the HTTP protocol. So what that means is that we insert these two parts while not changing anything from the application side. So what that means is that there's a HTTP protocol, and then when we apply, when we change it from HTTP to HTTPS, we don't change anything from HTTP. Just plug in TLS. That's it. Full transparency. Then let's see the example. So suppose a user would like to talk with the server, then we do the TLS handshake, go over that 10 steps to have a secure communication channel. After that, we will have the encryption and MAC key. So the structure is something like this, right? In this case, if I want to send the GET message to the server, I'll just send that to my TLS module, and then that will be encrypted like this, and then it will go over the internet like this. And then the TLS module at the server side, it can decrypt it, and then server just see the HTTP message. So from the server's perspective, it's just HTTP. Yeah, their behavior never changes whether there's an encryption or not. And then there is a result, and then that is going over the same path in reverse way, encrypted. And then it goes over the insecure internet, and then will be decrypted at the TLS module, and then will be available to the user application. Yeah. Any questions about how TLS works? Yes. So for the browser side, it's part of the browser. For the server side, it's part of the web server. So for example, Nginx or Apache, that kind of web server has the module called the Apache as a mode SSL. Yeah. If you enable that, then that will actually adding this kind of module right after the HTTP protocol. Yeah. So this is the example HTTP packet. So I tried to connect to the google.com this morning. Yeah. And then you will see that my request is red marked one, and then blue marked ones are like all the server side content. And then these are all plain text. So if we can see this, then all the middlemen can see the same content. So if we use HTTP, that's insecure. All the middlemen can see this kind of information. And then this is HTTPS packets. Yeah, the data is encrypted. So this is actually the get/HTTP 1.0, the same message the client sent, but it will use TLS 1.2. And then before sending this one, so you can see that the change cipher spec or something like that. So they did this kind of the negotiation and then communication. And then after having the change cipher spec on the client and the server, then client send the encrypted data. Yeah. So while we can see this kind of the plain text request in HTTP and in HTTPS, we will see the encrypted data like this. And then this can be done by just having TLS module, not changing the application. That's it. And then this is the stream of the TLS negotiation. Yeah. And then when I connect to the google.com, so some sort of the metadata, google.com, this kind of information is leaked. Yeah. So we cannot protect that information, but we can protect the further communication. Yeah. So the middleman might know that I'm communicating with the google.com. Yeah. But they will never know that what I have sent to Google, what I'm doing on the Google, something like that. And then this is another example of the encrypted data. Yeah. So this is not the encrypted data. This is the packet contents for the negotiation part. So the client hello includes the target server name, google.com, and then it will use HTTP 1.1. So that kind of information is written in the protocol message for TLS. But when it gets to the encrypted communication, So we will all see these kind of the encrypted value. So there's no plain text at all. Nothing about the google.com or something like that. Yeah. Then what's good about TLS? So internet is insecure, but using TLS, we can establish a secure communication channel over the insecure internet. And then authenticity, confidentiality, integrity, that's good. But the most important part of enabling this technology is, I believe, is the PKI. So for like a confidentiality and integrity, so if we can generate the key, then there's an algorithm, so we can use it. But so one people write algorithm, then it will work. But for PKI, we need to build that as a community. Yeah. So the among these like 3 properties, the most difficult thing that we can get is having the authenticity, and then thanks to PKI and digital certificate and that kind of structure developed from 1995. So now we can rely on that as an infrastructure for establishing the secure communication channel over TLS. And then another good thing is applications don't have to change their protocol. We can just plug in the TLS and then don't change the application and just sideload it. Then the application can enjoy the secure communication channel. And then we have an example that how can you make HTTP secure? It's just wrapping with the TLS. Then that's HTTPS. That's it. Yeah. And then how can you use TLS? So the TLS is available for in the most of the languages. There are libraries. So if you're using C and C++, OpenSSL or libsodium might be the one. And then if you are using Java, there's a library called Bouncy Castle that's open source, and then you can use like all the TLS or Cypress suites in there. And then the Python or other languages, they do also has like the SSL library. So in Python, the name of the library is still SSL. And same thing happens in OpenSSL. So even though the standardized name was TLS, so we still use the name of the SSL. That's why I'm always like the try to point it as a SSL and TLS. Yeah. And then to enable that, just wrap with SSL. And then I would like to show you an example of how that wrapping works. I wrote a very simple program, and then what the protocol is. So as a client, you need to send hello to the server. Then server will send a random number, and then client need to send the +1 of that number as a result. So hello, and then if they send 1000, and then I need to send 1001. Yeah. And then let's write the program for doing that. So this is the client part of the program. So we first create a socket and then type server IP and port to connect there. And then the protocol is that the client need to send hello first. So we send hello. And then the client need to receive the number from the server. So receive the data and then transform that as a number, integer, and then calculate the answer as that integer number +1, and then send that back to the server. And then receive the result. Result is either correct or incorrect. So this is a very simple program without TLS. And then this is a server-side program. So we create the server socket and IP port bind and listen, and then wait for this client connection. And then if connected, we first receive the 6 bytes of a message, compare that if that is a hello new line. And then if that is true, then it will generate the random number between 1000 and 10,000, and then choose one, and then send that number to the client. And then it will receive another 5 bytes, the 4-digit number and new line, and then transform that into the integer, and then that should match as a number +1. If that is mismatched, then it will send incorrect, and otherwise it will send correct. So it is just a simple ping pong server client like that. And then I will show you that how many lines should I edit if I want to provide a TLS to this protocol. So this is the source code diff result of the non-TLS and then TLS version. And then to enable TLS, what I did is I imported SSL package, and then after creating the client socket, I create the SSL context, then set up a little bit, and then after making the connection, context wrap socket. So after having the connection, we will wrap the socket with the TLS. So you can regard this as like the plug-in, the TLS at the socket. Yeah, that's it. And then when I plug in the socket, I change the variable name as a SSL client socket. And then that's why I need to change the socket name as a SSL client socket. But if I use the same name, not SSL client socket, just client socket for this, then I don't have to change these lines. So what that means is that, so just adding 5 lines of the code, yeah, it can enable TLS for the rest of the protocols. And then if I did not change the variable name, I don't have to change the protocol part. So right now the protocol is short. Think about it, protocol could be very long. We don't have to change anything. And then before starting the application, what we need is just initializing the TLS. And then this is the server part. For the server part, I use the same variable for the server socket. So I just imported SSL, and then set it up, wrap it, that's it. Yeah. So I just use the SSL server socket accept, but the rest of the part of the application remaining unchanged. So what that means is that when we try to adopt TLS, you don't have to worry. Just initialize it and wrap it. Yeah. Then you don't have to change the most of the part of the code for the application. That's the beauty of the TLS. So you have seen that from the internet layer model, there's a transportation layer and then application layer. Then we all actually sideload TLS in between the transport layer and then application layer. So that's why we call it as a transport layer security. Lecture for today was quite long. Yeah, thank you for your attention to the until the end. So let me summarize today's material. So interestingly, the internet is insecure by default. Yeah, there's no encryption at all. And then the TLS can transparently provide a way to establish a secure communication channel. So the transparency here means that we don't have to change the most part of the application. Just initializing the SSL TLS, just wrap it. And then the TLS uses digital signature, key exchange algorithm, symmetric cipher, HMAC, what we have learned. And then combination of that can provide the authenticity, confidentiality, and integrity. Yeah. And then we can enjoy this by wrapping the socket. That's it. But one of the caveat is that the default TLS only works with the TCP connections. But nowadays, like a Google Chrome or some other web browsers, they would like to change because TCP has a 3-way handshake, so that could be that could incur like a little bit of overhead on the network communications. So like the Google or some other like the server vendors, they would like to change the HTTP protocol to HTTP2 or QUIC or some other protocol. And then these protocols are not in TCP. They use UDP for the faster and then having a lower number of the exchange message. In that case, we need to use DTLS. So the UDP, the D stands for the datagram, and then DTLS here stands for the datagram TLS. Yeah. So there's a little bit of difference between the TCP and UDP for managing the session. So it's quite a little bit tricky to have a DTLS, but thanks to a lot of engineers worked on that so that we can just enjoy that from the libraries. So don't worry about the HTTP2 or create that kind of the datagram algorithm, datagram protocols. They can also be protected by TLS transparently. There is a, all right. So there is a question from Zoom side. So the NSA codebreaker A2, B2 challenges to really show how much effort it takes to keep your website secure. Yeah, that's also a good example because we will use a lot of the Wireshark, the application that shows the packet capture when solving the NSA codebreaker challenge. So like the challenges for this week will be a good example, a good practice for doing that. And then another question from Zoom was like when you wrap the socket, it goes through all of the steps we talked about just by wrapping it. Yes, that's true. So like the Python code, so initialization is like choosing the option, but the function call about the wrap socket, that actually do like a walk through the all 10 steps to having establishing the secure communication channel between the client and the server. Yeah. All right, this is the end of the lecture, but let me show you one thing in 2 minutes. So I want to demonstrate like how you can solve the challenges for this week. Just one challenge. Yeah. So I have released some challenges tagged with the TLS. Yeah, like this. And then each of the challenge will ask you to find some of the values in the packet capture. So you can download packet capture from this link. And then you can install Wireshark if you don't have from this link. And then if you have a Wireshark, then it will be opened as like this. And then each challenge has the description and then specific action you need to take. So what it says is like in the packet capture file, can you identify what was the client's random number in the client hello message in a hex string format? And then other question is like in the server hello, what was the cipher suit chosen by the server? It's something like a scavenger hunt and the packet capture. Yeah. And then all the challenges like that. And then to demonstrate how you can solve the first one. Yeah. So it says about what was the client random number. Then you can go to Wireshark and then go to client hello. Yeah. And then there's a part for the transport layer security. And then client hello message. And then handshake protocol. Then you will see that there is a random number. Yeah. And then this is actually the answer. And then right click, copy. And then if you copy the description, then and it has this kind of the information, but you can just copy and paste the hex string part. And then that will be the flag for the challenge. So please follow the instructions here, read the instructions, and then it's just like the finding the correct value and then typing the right answer. Thank you for your attention for today. Yeah, and then have fun with challenges. So the question is, are those all of the challenges for the week, or are those just for this lecture? So like on Thursday, we will learn about the password and the authentication, but I'm not sure that I can create challenges for that. So currently I'm planning on having no more challenges for networking, but I will create the challenges for the web server starting from next week. All right, thank you all. See you next time.